Okay, so here we are with the 11.1 paper 1 questions. Previous video was numbers 1 through 10, so here we are with number 11. Okay, so 11. We have a circular coil and it's moving into a field and then it's moving out of the field. And I can see based on the dots that field is coming towards us, coming up out of the page. And we want to know how would the induced current be. So as the coil moves into the field, coil at position 1 is moving into the field, and so therefore the flux is increasing, and so the induced magnetic field is going to oppose that increasing flux. So if the field is coming out of the current field, the field that the loop is entering, let's put it that way, that the field that the loop is entering is coming up out of the page, the induced current will make a field that will oppose that field coming out of the page to make a field going into the page. And so if it's going to make a field going into the page, here's my field going into the page, that's going to get me a clockwise current. Then as that loop exits the field, so we have the coil at position 2, the coil is exiting the field, so the flux is decreasing. So if the flux is decreasing, then the induced magnetic field will reinforce in order to backfill the loss. Because again, the Lenz's law says that the induced EMF, or the current that's induced, will make a magnetic field that opposes the change in flux. So if the coil at 2 has a lowering flux, then the induced magnetic field will reinforce what's already there. So that is going to make a magnetic field that is coming out of the page, and so that current direction is going to be counterclockwise. And so we have position 1, the current is clockwise, and then so no, and then in position 2, the current is counterclockwise, and so that gives us answer C. Okay, next question. All right, so for number 12, we have a rotating ring, and it's asking about the EMF. EMF is negative the change in flux over the change in time. They told us the change in time was time t, capital T, and I know that flux is NBA cosine theta, and is 1 ring, and then B they're calling X, and area they're calling S, and that's fine. And it wants to know what's the average induced EMF, and they're rotating the ring by 180 degrees, so 1/2 of a cycle. And the answer is D, and I'm going to show you why. Okay, so to begin with, it doesn't really matter if you say that the area vector is at 0 degrees to the field or at 180 degrees to the field, but that's how it starts. The area vector and the magnetic field are in the same direction. Why don't we start by saying that theta is 0. And so if the initial condition with theta is 0, then the flux is at a maximum. That would just be x cosine of 0 is 1, so we would just have xs over t, which is choice C. However, we are rotating the coil all the way around. The final condition is that theta is 180 degrees. And it was like, well, cosine of 180 is still 1. Or is it? Cosine of 180 is negative 1. And so if we go from 0 degrees to 180 degrees, we go from a positive excess over t to negative excess over t. And so the average induced EMF is the difference between those two, going from negative excess over t to positive excess over t, or vice versa. I don't even really care. That's double. That's 2xs over t, and so our answer is D. All right, number 13. Number 13 deals with Lenz's law. Man, so many of these questions deal with Lenz's law. Lenz's law is so annoying. Anyway, so when we complete this switch, that sends a current through the loop. And it honestly doesn't matter which way the current goes. Based on the setup and using conventional current, if we close the switch, the current is going to come out of the positive terminal of the cell and run, I guess it depends on the perspective. Looking from above, that would be counterclockwise, but I can draw that in. If I close the switch, the current's going to do that. And following the right-hand rule, that actually makes a north pole, makes the magnetic field point upward. So that's the north pole, so then the bottom side of that coil would be a south pole. But it doesn't matter, north pole or south pole, that is an increase in flux. I wonder if they chose capital Phi for flux on purpose, because it's directly related to the current in the wire, and current is I, and flux looks so similar to I. Whatever, doesn't matter. These are just kind of brain droppings from yours truly. Alright, so then we close the switch, that increases the current, and even though the magnetic field is up, that is an increase in flux. And so because of Lenz's law, the coil down below will seek to oppose that increase in flux. And so instead of creating a magnetic field that will reinforce, it will create a magnetic field that will oppose. That coil is like, nah, I do not like your magnetic field. I'm going to make an oppositional magnetic field. Now, in terms of attraction or repulsion due to those magnetic fields, we can label what the poles are. So yes, in the end, when the switch closes, then the two fields are going to repel each other. Oh, I said I was going to label the fields. All right, so if this is the north, and this is also north, and that makes this end south and south, but like poles repel. So when the switch closes, we have a repulsive force between the two coils. All right, but what happens when the switch opens? Then the current decreases pretty much immediately to zero because of an open circuit, but the current does decrease, so there's a decrease, a very rapid decrease in the flux. And so rather than seek to oppose an increase in flux, now we have a decrease in flux, so the induced magnetic field will not oppose, but rather reinforce what's there to try and backfill that loss of flux. So with an open switch, there's going to be an induced magnetic field to reinforce, and that actually would produce a attractive force. And so when we close the switch, there is a repulsion, but when we open the switch, there is an attraction, hence choice C. Okay, 14. So it says the current I flowing in loop A is increasing. So if the current is increasing, then the magnetic field caused by that current is also going to increase. And it's an increasing current, so that's an increasing flux. That is a flux change. So then there's going to be an induced magnetic field and current in B and C. And the flux from B and C, since the flux from loop A is increasing, the flux in B and C is going to work to oppose that increase because of Lenz's law. Okay, but what does that even mean, oppose the flux from loop A? So we actually have to look at, that loop right there and then see from that loop A, what magnetic field is it creating? So what is the current in loop A? What is the magnetic field that comes from the current in loop A? So there's the current in loop A, and following the right-hand rule for magnetic field around a wire. And as a result of that current, on the left side of that current, it creates a magnetic field going into the page, and on the right side of that current, from our perspective, it creates a magnetic field coming out of the page. And that magnetic field is increasing because the current is increasing. And so there will be currents in loops B and C that will be induced because of that change in flux, but those currents will create a magnetic field that will seek to oppose that increase in flux. And so the current in B will make a magnetic field that would not reinforce the inward field at that point from the current, but would seek to oppose it. So that purple magnetic field coming out of the page is what loop B would create to oppose the increase in flux from the original current from loop A. Meanwhile, loop C has a magnetic field coming out of the page. It wants to oppose that increase in flux, so its induced magnetic field would be going into the page. Okay, but the question is asking, what is the direction of the currents? Well, again, following the right-hand rule for loops, looking at coil B, if the magnetic field is coming up out of the page, then the current in that coil is going to loop counterclockwise in order to make that field. And then C, if I have my magnetic field going into the page, then the current to create that field would have to be clockwise. Okay, so the answer therefore would be that B loop has a current going anti-clockwise or counterclockwise. Boop, boop. And then loop C would have a current that is going clockwise. So the answer is C. Now this breaks across pages, so let's check the mark scheme, and sure enough, the answer is C. There we go. With no comment from the examiners. Thanks a lot, examiners. So there is 14. All right, next question, number 15. Okay, 15. So let's, it's talking about EMF, so let's remind ourselves how EMF works. So EMF is negative, the change in flux over change in time, or negative, the change in the number of coils times the magnetic field strength, times the area times the cosine of the angle between the area and the magnetic field per unit time. And so our coil is entering the field and then exiting the field. But while it moves through the field, even though the coil is moving, there's no change in the number of coils. There's no change in the magnetic field strength because it's a uniform field. There's no change in the area of the coil, and there's no change in the orientation between the magnetic field and the area vector. So while the coil is passing through the midst of the field, there actually will be no EMF induced. So that eliminates D. But we still have A, B, and C to deal with. Now, it's kind of like which of these things is not like the other. B has a positive EMF in the beginning and in the end. C also has a positive EMF in the beginning and in the end. C is more gradual, B is sudden, but A has a negative EMF and then it has a positive EMF. And the answer is actually going to be A, and it's not just because that's what the mark scheme says. You have to realize that the coil, as it enters the field, as we're entering the field, the flux is increasing. And so the EMF will produce a current that will make a magnetic field that will oppose that increase in flux. I'll just say EMF opposes. So the EMF creates a current, which makes a magnetic field that opposes, but that's going to oppose the change. But then as the coil exits the field, that's going to be a decrease in the flux. So the EMF is going to create a current that would make a magnetic field that would seek to reinforce the field, which is the opposite of opposing the field. So even just recognizing that difference, we're not going to have both positive EMF in the beginning and in the end, but instead what we're left with is choice A, where we have a negative EMF to begin with, but then we have a positive EMF in the end. Okay, number 16 of 20.
Yes.
Okay, so number 16 is extremely similar to number 12. We have a coil or a ring or whatever that is rotating in a magnetic field. The picture is different for number 12 and for number 16, but we still, if you imagine number 16, the magnetic field is kind of like going into the coil, and so that's the same is true for number 12. So it's very similar. The only difference in 16 is that 16 has a coil of n turns, and number 12 is just a single ring. So that would be a coil of one turn, like n equals 1. So we have, we already figured out, phone call. Okay. That was Ms. Nisler looking for Ms. Coleman. Anyway, so number 12, we kind of figured out about how the angle changes. We go from 0 degrees to 180 degrees. Cosine of 0 is 1. Cosine of 180 is negative 1. So in that shift, we pretty much have, if E is the change in the magnetic field, like NBA cosine theta, in 12, for some reason, the ring area was S and the magnetic field is X, but we figured out that it was for each, for each 90 degree shift, there was one excess in terms of the EMF, but it does that twice. So in time t, it has two 90-degree shifts, so that would be 2 excess over t. But we already figured that out in number 12. It's the same exact principle in number 16, except instead of X and S, they actually use B and A, as well they should. So let me actually rewrite. We have EMF. Let's see. And then for some reason, instead of doing NBA, they're doing BAN. That's fine. And just as in number 12 and number 16, we have a 180-degree turn. So that's going to be 2 BAN in a time t. And so that gives us D for our answer, 2 BAN over t. Pretty much the same question as, like I've been saying, the same question as number 12. See number 12. And, but we're using B and A and T instead of X and S and capital T. And also, one difference here is that this coil has N turns, so we include the number of turns, we include the N in our answer. And so that's 16. And then number 17, finally an easy question. Units, right? So magnetic flux is measured in Webers, so the answer is not A or D. And then magnetic field strength is measured in Tesla, and so the answer is B. Wow, that could not be any more straightforward, if only all the paper one questions were like that. So, number 18, oh, look at this. We have some kind of arrow situation. This looks like tons of fun. All right, let's give it a go. Okay, so 18 is actually a force on a wire question. This coil already has a current, and it wants to know what is the force on that wire. All right, so here's a left hand, or sorry, a right hand. It's a right hand. Maybe make the thumb. Yeah, that's a little bit better, I guess. But so, and the way the force rule works is that the thumb is going to be the current. So that is, make that red, I guess. And then that's the current. All right. And then the magnetic field are the fingers, and they're going into the page. So the mag field. So the fingers of the magnetic field going into the page is my little three-dimensional arrow. I can get rid of that arrow and just turn it into circle X. Here's the magnetic field going into the page, and so the force will come out of the palm. And so the force would be downward And so taking a look at this image here, I can see that the current direction is right here to the left. I can see that the magnetic field is into the page. And so therefore, based on the right-hand rule, my answer is D, that the force on the wire is downwards towards the bottom of the page. If we follow the current around the loop, the rest of the force, so if we follow the current around the loop, the force is going to be outwards. It's going to be pulling the loop apart, actually. But A, B, and C are not the correct direction. D is. You could probably also play which of these things is not like the other, but I guess you could also argue that B and D are the same thing, but they're kind of not. D is pulling outward, B is pulling inward. Anyway, the answer is D. Next question. So 19, we have another Lenz's law situation. We have a magnet approaching a conducting ring. It doesn't actually say whether it's a north pole or a south pole. I'm not sure that even really matters. So let's take a look at the image. And so we have an approaching bar magnet. Let's assume that the left side is a north pole, because why not? So we have an approaching north pole. Because of Lenz's law, the magnetic field that's induced in the aluminum ring will seek to work against that increase in flux. So the induced magnetic field from the aluminum ring is going to point against that. With the current, like so. It doesn't ask about the current, but I just figured I would draw that in anyway. So it makes an opposing magnetic field to oppose that increase in flux. Well, if I have an incoming north pole and the induced magnetic field has a north pole pointing the opposite direction, that's going to be a repulsion. And so if the barb magnet repels the ring is going to swing to the left at first. So that's A or B. But then what happens when the bar magnet moves away? So yeah, that would be moving towards the ring is an increase in flux. But if we take the magnet and move it away from the ring, so if we then move away from the ring, that would not be an increase in flux, that would be a decrease in flux. Flux goes down. And so if the flux is decreasing, then the magnetic field that's induced in the coil will seek to work against that. Whatever the change in flux is, Lenz's law says that the induced magnetic field will seek to move against it. So if the flux is decreasing, the magnetic field from the coil will seek to reinforce the field, will seek to backfill that loss of flux. So instead of making a north pole to the left to oppose, it's actually going to make a north pole in the same direction to reinforce. And so it'll make a magnetic field to reinforce. And so that means if the north pole is pointing to the left, that means the south pole is on the flip side, is over on the right. And so there will be an attraction between the bar magnet, the receding bar magnet, and the aluminum ring. And if there's an attraction, then the ring, instead of moving to the left, will then move to the right. And so our answer is B. And here's the last paper 1 question. So we have 3 conducting loops, and they're moving in a magnetic field that is dots, so that magnetic field is coming up out of the page. All right, so 20 is asking about the EMF that's induced. So EMF is negative change in flux per unit time, and so the flux is NBA cosine theta, and so they all have the same, it's all one loop, so it's all the same N, it's all the same magnetic field strength, so it's all the same angle orientation, and moving at the same speed, so it's all the same time. But the difference between x, y, and z is the area. The difference is in A. So if we look at x, and it says at the instant when the loops enter the magnetic field. So it's not saying in general, but at the instant the loops enter the magnetic field. The reason why that's important is because you might look at this question and say that y, and z have an area of 4 squares, whereas loop x only has an area of 2 squares. But at the instant they enter the field, x and y only have that one side. So at the instant they're entering the field, x and y, the side that's entering the loop, the side of the loop that's entering the field is only 2 squares, whereas loop z has 4 squares entering the field. So at the instant when the loops entering the field, enter the field, z has the most exposure. And so the answer is A, z only. All right. Well, that's numbers 11 through 20 from the paper ones for 11.1. Thank you.